Please.
Well, thank you very much. Can you hear me? Ich hätte gern nach Deutsch sprechen, aber ich habe versucht und nach 10 Minuten ich habe gedacht, nein, das kann ich nicht machen. So deswegen, ich versuche auf Englisch zu sprechen und hoffentlich Sie verstehen alles, was ich sage. Natürlich Fragen nachher kann auf Deutsch sein. Wenn ich das nicht gut verstehe, bitte wiederholen Sie das. So, mein Topic heute ist der Antikythera Mechanism, which is quite outside my main field of research, which is pulsars. My career started here in Bonn. Professor Seiradakis, who is among the audience, is the person who offered me the first postdoc. It's very important to get your first postdoc. And after that, of course, everything went easily. I have some friends here that I'm very, very glad to see them. Professor Kuhn, Professor Sieber, he came from Krefeld. Roland Greve, I don't want to start talking about my friends here, I had many. Okay, Antikythera Mechanism. My first question is why the Antikythera Mechanism is such an important artifact. I think the first thing is that it is the oldest calculator known in the world. It was built about more than 2,000 years ago. It was a calculator with all the meaning of the word. For example, it had input, it was making calculations, and it was giving the output on scientific scales, so not only qualitative, but quantitative. This is very important. Now, how does a gear mechanism make calculations? It's very easy. If you take a gear with 20 teeth, and you connect it with a gear with 10 teeth, when the first one does a full round, the second one has done 2 rounds. You can multiply by 2. If you join 2 or 3 or 4 or 5 gears, you can do any calculation that you like. Divide, calculate. It even has differential calculations. I will show you how. So, for example, it has a point where it has 19 turns of one of the pointers, gives 235 turns of another pointer. These are astronomical periodicities. To me, this is as important for the evolution of technology as the Acropolis or the Parthenon for the evolution of architecture. A very important artifact. We have to write new books about it. We have been asked often by friends, people from abroad, if we have some photographs to give them because they're rewriting their books of technology. And it demonstrates the unexpected technology of the ancient Greeks that we did not know up to now. We knew that they were very good in poetry, in writing, in mathematics, physics, astronomy, architecture, etc., but not technology. And here is this artifact, unique in the world. It took 2,000 years, sorry, no, 1,500 years, so 1,500, to build a device which is as complicated as this one, with gears, of course. And what was it? And what did it do? It was, as I explained, a very good geared astronomical computer. It would calculate the position of the sun and the moon on the sky, and probably the planets, most likely the planets as well. Because of this, it will calculate and foresee eclipses. Eclipses happen when the sun, earth, and moon are aligned. If the earth is between the sun and the moon, you have a lunar eclipse. If the moon goes between the sun and the earth, you have a solar eclipse. So this is the way that they calculated eclipses. They could foretell eclipses because they know the position of the sun and the moon fairly accurately. It has a social face as well. It has on it a pointer that shows when the Olympic Games should start. The Olympic Games in ancient times were starting on the first full moon after the longest day of the year, the solstice, the summer solstice. So that was again an astronomical event, and it was easily calculated. A very complicated device, so the person who actually made it, he built in a proper user's manual. This means that the person that was using it was not the person that actually made it. I know that you have already some questions, but maybe we'll do it at the end. At least I will have asked some questions at this stage. How did it work? So I have 3 slides that you see with why, how, and why, where. What is the clock mechanism? So it's like our clocks, our watches that we actually turn a knob or something and then they work for a day or two. Did it have, if it was a clock mechanism, did it work with a clepsydra, you know, the thing that lets time be counted by measuring how much sand goes in a little pot? Did it have a counterweight, like the old clocks of our grandfathers and fathers? Did it have a spring? We haven't found any of those. It was manually driven by hand with a knob. This is the first, we are sure about it now, except that we have recently found that it was driven from the front plate and not from the side, and this is very new. We have calculated 2 things. Well, we have calculated one thing, and this is the moment between driving from gear to gear, and B, because when we built our models, it was so easy to turn it from the front plate, and it was very difficult to turn it from the side. Let me go back 2,000 years ago. Between 75 and 68 BC, a very large boat, an old cass. It was very large. According to one of the archaeologists, who is a very famous Mediterranean diver, Bernard Foley, it was the Titanic of the time. It was about 40 meters long and about 50 meters, 30 to 50 meters wide. One of these large boats that brought wheat from Egypt. Of course, immediately this raises a question to me, in which port could this boat put anchor? And there are very many, but no one has managed to answer this question as yet. The boat was full of artifacts, eventually did not make it. Reaching the gap between the sea, between the Crete and Peloponnese in southern Greece, the boat sank just outside the island of Antikythera. You can see it here. Antikythera has a very nice port here in the north side. The boat sank about here. So maybe it was trying to reach the port, but it did not make it. As I said, it was full of art and other precious artifacts. Also, it had a lot of merchandise. Until about a year ago, in my lectures, I was saying it was full of precious art and artifacts. Now, after last year's marine excavation, the archaeologists told me that they found lots and lots of merchandise, and this is amphora, pithi, and other things that they would transport between cities. 2,000 years later, it was 1900, in fact it was Tuesday before Easter, 1900, 2 Simeon from the island of Simi, which is just north of Rhodos. This is Rhodos, this is Turkey here, and this is the island of Simi. On their way to North Africa to collect sponges, these 2 boats, they put anchor on the Potamos harbor of the island of Antikythera, and for some reason, the archae-diver Elias Lycopandis, this is a photograph that a niece of him gave us while we were in Rhodes, died just outside the harbor. And maybe he was asked by the Captain Dimitrios Kondos, come on Elias, could you please dive down in the sea, collect some seafood that the Greeks are allowed to eat during fasting days. It is almost Easter, we should be fasting, but let's have something nice to eat. And instead of bringing seafood, he brought up the bronze arm of a bronze, supersized bronze statue. They had to go to Africa because they had to pay for it to collect sponges. They came back in August, or around there probably, in the island of Sini, and there, after consulting all the people, they decided to come to Greece, go to the Minister of Education that was responsible for culture as well, to show what they had found to the minister. The minister's cousin was the director of the Deutsches Museum of Athens. So he came there, they realized it was a very important finding, and within 2 months, at least for modern time in Greece, it is unheard of, they organized a full expedition to dive and actually investigate the shipwreck. You can see here, this is one of the, please notice that I see my mouse here. You cannot see, mouse. Okay, here it. I have my hand. You can see here one of the diving suits that I photographed in Sini. When we went there to pay, we went there to give a talk. And please notice that the water is very deep and the shore is very rocky. The shipwreck was found 50 meters away from the shore and 50 meters down. It was a very steep 45 degrees inclination at the bottom of the sea, to the bottom of the sea that goes all the way to 200 meters or maybe 250 meters down here. My mouse seems not to work properly, but let me see why this has happened. Something has happened here. No, it should be working. Okay, doesn't matter. Here you can see some photographs from the diving in 1900. Here you can see some of the statues in very bad condition, most of them. They were drawn up. About more than 100 statues were brought up from the shipwreck, many of which are shown in the atrium of the Archaeological Museum of Athens. If you go down the steps to get a cup of coffee, all the statues, the marble statues that are around there, they were actually from the Antikythera shipwreck. This is one of the nice bronze items that he brought up. We call it the head of the philosopher of Antikythera. This is one of the most beautiful bronzes that we have in the Greek museums, the Antikythera youth. There's a very nice glassware. This is Mirafiori technique, so the ancients they did know how to seed metals when they were making glass out of sand, effectively. Nice jewelry, and for some reason the divers brought up something that was maybe a bit heavier, it looked a bit green, it was standing out on its own. They put them in a box. This is one of the marble statues that is pretty good. In fact, look at it. The right side of the statue is almost beautifully preserved, but the left side is heavily damaged. Did the microorganisms in the bottom of the sea prefer the left side of the statue and not the right? Of course not. The right side was stuck in sand, and so it was protected. But as I said, the bottom of the sea was very steep. Sand would not have stayed there for very long. So it must have been the ballast of the boat that they had wedged the statues and everything else so they did not break on the long journey. This is what saved many of the artifacts there. Newspapers started writing about the Antikythera shipwreck in November 1902. This is the first item that we found after searching 5 years, a complete search 5 newspapers at the time, a complete search for 5 years. We found more than 400 clippings, many of which are for the Antikythera mechanism as well. I think that the Antikythera mechanism was brought up to the surface of the sea in 1901, towards the end of the diving season. And it was recognized as an astronomical device in 1902, when we first called it the astronomical astrolabe. We know now it's not an astrolabe, it has gears, but it is something that they recognized at the beginning. A British subject, you know something? I don't know, something's happening here. Doesn't matter, maybe it's okay, don't worry, I can wait behind. Thank you so much. Derek the Solar Prize, a British citizen who was working at Yale University in the United States at the time, he heard about gears, metal gears made 2,000 years ago. Now he was a philosopher of sciences. People say that he had read all the several thousands of books about the time. He had never heard of gears so early, so he took the first aeroplane, he comes to Greece, he gets the permission from the Archaeological Museum, gets the help of Karakalos from the Democritus Center in Athens, close to Athens, and they make the first radiographies, as they say, probably hard X-rays or soft gamma rays. And through the one of the fragments, they see many gears. Of course, they started counting the teeth. The wife of Karakalos is reputed to have made very careful measurements there. And eventually he goes back to the United States. He makes a model. He works there for 30 years. He makes a model that his nephew told us he was taking to schools and cities in the United States, explaining how advanced technology they had 2,000 years ago. We know that he made some mistakes, but without him, I wouldn't have been here today. Let me say just one slide to mention Jacques Cousteau, because he came in 1953 and 1976. In 1976, he actually made a proper dive, and he brought out several items, among which some coins from Pergamon, Ephesus, that were dated between 78, probably 75 and 68. One of them may be 60. BC, but this is the upper limit of a shipwreck. So we know about the shipwreck that was before it was BC. After Price, another Brit, Michael Wright, an Australian, Alan Bromley, they started investigating the mechanism. Unfortunately, Alan died a couple of years later, but Michael, who was a person with good imagination, he started working on it, measuring, studying, publishing. Unfortunately, he had been publishing in radio, in journals that no astronomer reads. So he did not know very much about it. However, he is a man that has done lots of good work. Here you can see sitting in front of the Technical Museum of Thessaloniki, holding proudly his model of the Antikythera mechanism. The front side is shown here to the right, and the back side of the mechanism is shown here to the left. He is the first person that realized that what you see here as circles, they are actually spirals, and that is very important. Okay, from 2001 onwards, a very large multidisciplinary and international team is formed. 5 people were, I think, the core group of this people. Archaeologists joined us soon after, a paleographer, and many other people. I will not go through, just skip this until I show you some of the fragments. The Antikythera mechanism nowadays consists of 82 fragments, 4 of which are shown here, the largest one, and maybe the most important one. To get an idea, the largest one, fragment A, is 15 by 16 centimeters, and the rest is smaller. They are all here. Fragment 19 that I have here sketched is something that gave us new insight. And here is what probably the mechanism looked like. In the front it had 2 concentric circles, dials, and in the back it had two spirals. I'll talk about them later. Techniques that we use. First of all, from the United States, from Hewlett Packard, Tom Maltzbander came with his dome. You can see it here. You have a camera there. You put at the focus of the camera, you put the fragment that you want to investigate. You switch the light off. Inside this had 50 bulbs, like bicycle bulbs, not very strong, but they give some light. And after switching off the lights, you press enter on his laptop, and one by one the bulbs start shining, and the photograph is taken by this camera. 50 lights, 50 bulbs, 50 photographs. Neither the artifact, neither the fragment A as it is now here, nor the camera have moved. So what is the difference between the photographs? That the light comes from a different direction, depending which light, which bulb is lit, and the intensity is different. Because of this, though, Tom written a very nice algorithm, mainly for children's game, but it was used here. And you can see here fragment 19 that I mentioned earlier. You can see some lettering there. All of it in, all the letters from the Antikythera Mechanism are in Greek, that I can easily read. The technique of Tom Maltzbander makes everything very clear. Every little dent on the surface of the fragments can be easily read now. Examples. Soon after, a couple of months later, another a tomographer, X-ray microfocus tomographer, came from Tring, England, just outside London. We had some difficulties actually bringing it into the cellar of the Archaeological Museum. We had some help, and here it is already set up. Fragment A is here on the turntable, and now the turntable starts going around. The X-ray gun is here on the left, and the detector, SCD, is here to the right. As it rotates, every half a degree, or even earlier, we take a photograph. So we had a full coverage up to 370 degrees really, so we have an overlap to make sure that the calibration was not lost in between. And so we had X-rays. We used a very able program from Germany, very expensive, but I thank my university for buying it, because you could do actually measurements with this program, not just seeing. These are some examples of the tomographies that we have. Excellent quality, as you see. Everything that the archaeologists of the old times, of 1900, did not actually manage to scrape off in their attempt to find what is underneath the calcified material, is very clear and very well preserved. This is fragment D, and this is fragment A. Fragment D, here on the left, it would be like this. We may kick it on the sand if you see it, but inside it has a very well preserved gear with 63 teeth. Until about a couple of years ago, we did not know what it did. We do know now. And this is fragment A. You can see how complicated it is. It has 27 gears in it, all meshed together. Let's move to the next slide. Okay, we have a puzzle and we have to solve it. Let's go to the front plate of the Antikythera Mechanism. It had, as I said, two homocentric dials. The outside had 365 divisions. Of course, this is a calendar, a yearly calendar, divided into 30 sections, bearing the names of the months in the Egyptian language in Greek letters. It's like Greeklish, as we say today. The inside one had 360 divisions and had the names of the zodiac constellations as we speak them today in modern Greek. Please notice that there is something here that at the beginning you don't know what it was, and then you found a writing, you found actually the text, evidence for it. It was a small spherule, a little sphere that was painted black and white. As the user turns the knob and all the gears move around, this pointer here goes around and shows the position of the moon in the zodiac scale. And there is a crown gear here that actually rotates the axle of the axis of the moon around it. It does this. And as this sphere is there, it turns around with it. It was painted half black and half white, showing thus the phases of the moon. Black is new moon and white is full moon. Please notice also something else. There is the outside dial was detachable. We did not know this at the beginning, but when we started going with X-rays down after about 3 or 4 millimeters, we saw there was something stopping there. Here there is also something peculiar. There was a pin there. All this we did not understand to start with, but now we do know what it is, because underneath this detachment dial there was 365 holes, very carefully made, 0.6 to 0.8 millimeters in diameter. And okay, having now this evidence, we realized that every 4 years the user could detach the dial, rotate it by one hole, put it back again, taking thus into account leap years. So it was a calendrical machine. It was a very accurate one as well in this respect. Let's go to the back plate and investigate the upper back dial. This one here, it is mainly seen on fragment A, B, and mainly these two, I would say. When we checked it, we found it had the upper side was a spiral. It had 235 divisions, and it was full of letters. 235 divisions is a well-known astronomical periodicity. Every 235 lunar months, from full moon to full moon. The moon comes at the same zodiac, the same part of the sky, and has the same phase. If somebody knows the Metonic periodicity, as it is called, then he can calculate well in advance, several years in advance, the phase of the moon, which is very important in ancient times, because they did not have a switch to turn night into day, but they were working with full moons. Okay, so this is the upper back dial. It had the Metonic cycle. It had also in there a subsidiary, a smaller dial with 4 divisions. I will explain what this was later. Let me go on. And it had a pointer. I'd like to stop on this pointer because recently we found that it was not a simple pointer. It was specially constructed. I'm trying to actually give you the story and the research as we were doing it day by day or year by year. So the pointer was going around, it had a pin in there, and was going through the gaps of the spirals, and as it was moving around, it was showing each month of the 235, as I said, so the user knew of which month we are. Because this is a spiral, the arm of the pointer should be sliding inside and outside. The spiral is actually, the radius increases as you go from inside to outside. And our first reconstruction was what you see here, but later, with the help of Lina Anastasiou, who did a PhD, the first PhD in the world on the Antikythera Mechanism, we have found that it was complicated and reasonably constructed. This is the shaft that actually rotates, around which rotates the pointer. The pointer is here. It had an inverse pie shape device that was snugly fit on the axis. It had 2 holes. This is what I'm telling you now, we found on the user's manual as well. In the upper hole, the pointer was sliding. In the bottom one, there was again a pin was going through. And on top of it, it seems there was a head cap. Now the whole construction is that you put this down like this, and this is now, you can see it fully constructed. The cap goes all the way down and fits on the shaft. The pointer slides on top of it, and in fact, at the very top it had 4 well-inscribed holes. Most likely it was to put some kind of grease, maybe fat, in order for the pointer to slide easily. Let me go now to the lower back diet of the Antikythera mechanism. It was mainly fragment A, E, and F. Let's investigate a little bit this spiral. When we counted how many divisions it had 223. I will show you some of the divisions with zoomed photographs later, believing that the counts are very accurate. Again, this is an astronomical number. It's every 223 lunar months. We call them synodic months because there's a synodos between the sun and the moon every month, which lasts for 18 years, 11 days and 8 hours. Every 223 moons, eclipses of the sun or the moon, they repeat with the same characteristics. For example, if today we had a lunar eclipse, and after 14 days we had a solar eclipse, and after 6 months we had another solar eclipse, and after 20 days we had another lunar eclipse. After 223 lunar months, so lunations, we will have again a lunar eclipse, 14 days later a solar eclipse, 6 months later another solar eclipse, and 20 days later another lunar eclipse. Whoever knew the solar cycle, he could predict eclipses. We know that ancient Greeks could predict eclipses. Herodotus mentions the battle between the Lydians and the Persians, if I remember well, in 585 BC, where he told the people, the soldiers or the generals, that if you continue with your battle, good God is very angry with you and will take the sun out of the sky. So the good God did take the sun out of the sky, and the battle was stopped. The battle was stopped. And this is one of the stories of Herodotus. Okay, and there was also a subsidiary diet with 3 divisions. That is also very important, and will tell you exactly what it is. As I said, as I have written here, the 223 lunar months are 18 years, 11 days, and 8 hours. This is important for 8 hours, because if you have an eclipse, say in Babylon, after 223 lunar months, the next is going to happen 8 hours later, or 120 degrees later, probably in Spain. Then after another solar cycle, it will happen in the other side of the world. And only after 3 solar cycles, you come back to Babylon. This is a cycle of 54 years, known in ancient times. It was called exeligmos. Probably you're surprised that the ancient, they did know all these long periodicities. The Babylonians were the first ones that actually wrote down eclipses and other astronomical phenomena. The Greeks put some more data in it, and then being good geometers, the Babylonians were very good in algebra, but not in geometry. Please remember Euclid, for example. They could start making predictions. Let me have a look now at the fragment A and F, maybe F. Again, if you see it on the road, you may kick it, it doesn't look very impressive. But look, if you go down a few, this is about a centimeter because it is a lot of calcium on it. And you start seeing the spirals, you go a little bit further down very clearly, and you start seeing division, you start seeing some letters. I will probably show you some letters later, but let me go to magnification. Now here you can easily see what I mean by divisions. You see some letters, not in all the divisions. Some divisions had letters and some didn't. In fact, they didn't make a sense. They didn't have words, just letters and numbers, and some symbols. But as we were sitting out at midnight after a long day in Athens, drinking a retsina and a souvlaki, we started talking about it. Tony Friedrich was the first person who actually proposed that this has to start to do something with eclipses, and And then Xenophon Musas and myself, who speak Greek, would start seeing something more about it. Let me show you though some of this, to paint some of these symbols that were engraved in the spirals. There's an eta, that's an anchor-like symbol here, a sigma is here, another anchor sign. The same, the anchor sign is always there, and eta again. There are probably some numbers like epsilon, this is probably the number 5, etc., etc. Now let me go to fragment A, at the bottom right back side. Again, you can see the division pretty well. I must say you have a very good projector here, because sometimes I have problems showing this to people. Again, we have engraved coded numbers and letters. These are again a sigma, an anchor-like, etc., etc. Now let me show you all the places you have found something. And in fact, there's a new one somewhere here. Okay, let's it shows another ellipse. Here are 16 of them, 4 times 4, that had, let me clean it a little bit. You can see again the same letters, the eta, the sigma, the anchor-like, the same, and me, eta, sample, numbers, and then we realized with Xenophon that eta should be the first letter of the word Ilios, which means the sun. Sigma is the first letter of the word Selili, which is the moon. And then soon after we found that this anchor-like symbol were the first 2 letters of the word Ora. It was an omega and rho. So when the pointer reached one of these divisions with symbols, it would warn the user that an eclipse, a solar or a lunar eclipse will happen at such time. The month is known from the Metonic calendar and also from the Saros spiral, but also then the user could go in the front side and see the 2 pointers, the lunar and the solar pointers. If they were opposite, it means that the Earth is in the middle, and then we have a lunar eclipse. If they were together, it means that the moon is between the sun and the earth, and then we have a solar eclipse. So it was a very good calculator of eclipses. Impressive, I think, really. Now, there was a gear here that had 223 teeth. Originally, when we counted the teeth, we said 23 or 223 or 224. And then we thought, my goodness, 223 is a prime number, very difficult to divide the circle into 223 divisions. Probably, when this will be published, it is 224 divisions, which was wrong. We know now it is 223. That is the gear that drives the Saros pointer. Nearby, there were 2 gears of 50 teeth each, that you can see here. Easily recognized. You can see them here slightly better. There is a cut here. In fact, in the early research, people were saying this is probably broken and that this is an attempt to repair a gear, which of course is very important if you can repair gears in the ancient times. However, when we had a look with our good tomographies, and let me give you this here, in fact, let me go with my arrows. So this is what we see. Obviously, it is a well-cut slot. And now what I will do, I will go down by about 3.5 millimeters. There it is. Again, 2 gears with 50 teeth each. However, I cannot see the cut. Nothing there. Then go up and down and up and down. Obviously, there are 2 pairs of gears, so 4 gears, but they're one on top of each other. So 2 gears with 50 teeth here, another gear with 50 teeth here, another on top, another on there. Now, this is rather illogical because these gears must do exactly the same thing. Why did they have to have a cut? Why did they have to have it like this? Why did they have 2 gears, 2 and 2? Why didn't they leave them as 50, as only 2 gears? So we had to start investigating. We took a higher resolution tomographies, and here it is now. You can see to the left that the cut or the slot it extends all the way in but it is somehow blocked here. And in fact, we realized soon after what was happening. This is, the bottom one had a pin, and the top one had a slot. And as the bottom gear was engaged through the pin and slot to the top gear, it was co-turning it. It was turning it as well. But again, this is rather illogical, because again, it does exactly the same thing. Why did they have to have this difficulty there? And then we realized that these two gears are not homo-axial. They did not have the same axis. They were slightly off center. It was, the gear was like this. The bottom one was the axis was this one, and the top one was this one here. The difference was 1.1 millimeters. But because of this, as the pin rotates the upper gear of the slot, is engaged either to the periphery or close to the center of the gear, driving it faster or slower. So something like this. Let me go back a couple of times. So it is, the upper gear was moving back and forth because of its eccentric axis. You realize that this is a differential motion. And when we actually measured how fast they go, how fast they rotate, we found out that it was rotating at the same pace as the moon on the sky, with an accuracy of 1 to 200. The calculations were done by a mathematician, Elias Gurtsogiannis, who I think at the moment is in China. I hope that some astronomers here, they have realized that what I have been taught to all the time is Kepler's second law of equal areas. So they did know it. And when we looked at Ptolemy, we found that he refers to Hipparchus as being the first person to realize the first anomaly of the orbit of the moon on the sky. So Hipparchus, who I think was the best, the most able astronomer in 2,000 years ago, knew about this motion of the moon, and the moon stars seem to be going faster and slower, faster and slower. And this was simulated in this way by the ancient Greeks. Okay, now this is a profile of all the gears. You can see trains of gears, the one moving the other, etc., and eventually producing the back, either the Metonic cycle or the eclipse predictor, and for the extended mass as well. I did say something about a subsidiary dial inside the Metonic cycle, but it had 4 divisions. We started investigating it, and soon we found these large letters: L, alpha, beta, gamma, and delta. And a big graphologist immediately told us this means year 1, 2, 3, and 4. We knew that in ancient times the dating, the counting of dates was done often with the years of the Olympics. So they were saying this such and such king was crowned on the 3rd year after the Olympics of 775 BC. So we started looking for Olympia, but we didn't find it originally. But we did find the word Nemea, which is one of the 4 crown games of ancient times. Of course, this was every 2 years, and opposite we found again easily the word Nemea. We knew how to look now for the East, for the Olympiad, and we found the Olympia here. We had 4 years, so it's only one. Opposite was the Pythian Games in Delphi. And the 2 years, the games of the Isthmia close to Corinth were also there. We were surprised, though, to find the Na games, or Naya. That was the games of the Naos, of the Dodona Naos. And that was something that we did not expect. Did the Antikythera Mechanism has any connection with northwestern Greece? Maybe something had brought it there. Recently, it has just been published by Paul Iverson, although we know him because Paul had come to Thessaloniki, we did work together for a long time, and he just published that here we have the Aliyah, which are the games on roads. We are very glad to find anything about roads because all the archaeologists point at roads as the best laboratories of that time. So, but we haven't been finding anything about roads, so this is the first evidence that we have really have found there. The Antikythera Mechanism probably had two, or we have found remnants of two porticos, of two doors, covering the front and back plates. And most of the 3,400 letters that we have read and decoded up to now, they were inscribed on these two doors, on the bronze plates of these two doors. Here you can see a little bit about the dimension of the Antikythera Mechanism, which was 32 centimeters high, about 16 centimeters wide, and the depth was probably between 8 and 10, maybe 20 centimeters, sort of like a laptop of nowadays. It was portable anyway. Now I'm going to say something that, give you something that I have not published yet. We have written it and we have found a mistake, we have to correct it, but I hope we'll have it ready in the next month or so. Inside fragment B, the one I showed you on the left, that had a 63-tooth gear in it, there's wedged on it, there's a kidney-shaped or bean-shaped part, which we have about 3/5 of which. And we do not know what it is. We call it item X when we're talking between us. And then when I was talking with our mechanical engineer, Professor Seiradakis, relaxing in a boat in fact, he told me that this must be a cam. And of course, me being an astronomer, I did not know what a cam is. So I asked him to explain to me. And he said, do you know, have you ever seen the engine of a car? I said, yes, I have opened my car. I have opened the engine of my car in England. I had a very tatty old Hillman at the time. I had changed the head gasket and everything quite often. So yes, I know what a camshaft is. A camshaft is exactly what I showed here. It opens the valves. As it rotates, it opens the valves of the pistons so the car can move. Now this is an example of a cam. You see as this rotates, it starts with a small radius, larger, 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 largest, and then it drops down again. A curve described by this radius, or this radii, is something like this zigzag curve. So I understand now what Kyriakos means, and my task is, of course, to find an astronomical periodicity that could be simulated with this cam. Of course, we have to assume that it's symmetrical, otherwise we couldn't work on it. Most likely it was. We started taking measurements. I would not go, sometimes engineers explain this a bit more. We measure carefully the distances, these distances here, we put them in tables, and after assuming it is symmetrical, we thought that we start having some idea of what is the curve described by this cam would look like. So it was a curve with two maxima and two minima. So the two maxima come from this long side part of this item, and the two minima come from this axis. Okay. The first thing that I thought, of course, that the sun, as you know, rises and sets exactly from east and sets to the west only twice a year during the equinoxes, in 21st of March and 21st of September. In the summer, it rises much further to the north, and in the winter, much further to the south. So the sun rises, let me give you a picture of it. The sun rises not exactly from exactly the same position of the sky, of the horizon, but moves like this. Here it stays a bit longer, because it goes back and forth, but much faster through the equinoxes, and stays longer on the other side. So, okay, I have now something that has slow and fast movement. It has twice a year. So I gave the data to Kyriakos to see if he could simulate it. And after about a week, he came back and said, I need another curve. I think about the retrograde orbits of planets, like Mars, for example. But Mars goes slower than the stars. The stars goes backward, but every now and then goes a bit forward and back again. So this again has 2 minimum, 2 maximum. I will not explain this graph, but this is because the Earth moves much faster when it's orbit around the Sun, not Mars, which is a bit outside. Kyriakos tries it, again, failure. Okay, now I had another idea, but this was a tiny movement. This is the so-called equation of time. I will explain what the equation of time, although any astronomer here will probably find it boring because he knows what it is. You have seen an equation of time if you have ever gone to the Astronomical Institute next to the Max Planck Institute, where there is a sundial and there is a curve there that shows the equation of time. Let me explain now what the equation of time is. Every year, our watches, or the small pointer of our watches, goes around 365 times 2, so 730 times. And of course, our watches did not go, they flow smoothly. So time goes smoothly as we count it with our clocks and watches. This is what we call a mean time, but the important thing is that this time is measured by clock, flows very smoothly, regularly. In reality though, any time is measured by periodical phenomena, and there are not very many in nature. One of them is rotation around an axis, like the Earth rotating around its axis. Another is rotating around another body. This is like the Earth rotating around the Sun. There could be periodicities with oscillations, and also some quantum effects, but I will not talk about it. Okay, so we know now that the Earth does not rotate evenly, around the Sun. The reason is A, that we measure time on the equator and not in our latitude. For example, we measure time by measuring how many minutes are passed between sunrise and the next sunrise. If you're in the North Pole, you cannot measure sunrise and sunrise quite often. You realize that you have to measure something on the equator to be able to have a consistent timing. Furthermore, the Earth's orbit around the Sun is elliptical, and as such it goes faster in the perihelion and slower at the aphelion. Closer to the Sun goes faster, and away from it goes slower. Again, Kepler's second law. Because of these effects, the time which is shown by sundials, which you call apparent solar time, does not run smoothly. Either faster or slower, only twice a year it coincides with what our clocks and our watches show. So we call this apparent solar time, whereas the time shown by our clocks is called the mean solar time. Now this is the equation of time, analyzing the two effects that I have told you. The solid curve is the equation of time that goes back and forth by plus or minus 15 minutes from the smoothly shown time from our clocks and watches. See, the idea now is that if we apply this somehow to the point of the Sun, this should be going back and forth a little bit for a mean value. But it takes a year to go through 160 degrees, and of course 15 minutes in a day, it's nothing, you couldn't see it. But Kyriakos, being an engineer, he thought of another way of actually showing the equation of time on the Antikythera Mechanism. So we went through some calculations, and eventually we came up with an idea. I will not explain this. This is probably what I will stop here. As this gear, as the gear of 63 teeth in fragment D is moved by another gear of 63 teeth, which you have not found. Many of the gears of the mechanism are not found. But if we know the effect, we know what they should look like. So as this moves, it correlates, the cam correlates with the gear, and if you have a pointer moving, joint here at the edge of this cam, then this will be moving up and down. And in fact, I can show you a little video. I hope it will play. Let me go here. Okay. Yes, here it is. Let me start it. Good. Okay, now here you can see how the cam rotates and the pointer going up and down. With blue, I have put the equation of time calculated for the year 150 BC, so around the Ptolemy time, about Antikythera Mechanism time. Ptolemy was a little bit later. And this is the calculation that we made with this device. So let's stop here. Did I stop it by mistake? Yes. I think that the coincidence is fabulous. We have not published this yet, but we are going to publish it soon. We know now how many gears we have. We cut them. We assembled them. It took us several nights and days, of course, assembling them. We made our first model. It is not operational. Our second model, semi-operational. And from now on, we know exactly how to do models. And in fact, we can calculate any model anybody wishes. And we do get orders from museums to build a model for plexiglass, for example, 3-to-1, that somebody can actually use it and see how all the gears inside they rotate. And so we are an expert in this by now. And I will close with something again that has not been published, although the evidence has always been there. Did ancient Greeks have machine tools made from hard metal so that they could cut gears and shafts? A question that usually I was asking in talks. So we started searching the literature again, and we found that in the Museum of Elefsis near Athens, there is an inscription that refers to an order to make empolia and polus, I will show you what these are, for the temple of Philonia Stoa. Now, what are the poles and the empolia? So the poles are these little things that you see here, the little thing that you see here, and the empolia are this one here. So when you make one of the columns, we do not make it in one piece. We make it in several pieces. And then you have to put them together, assemble them, and make sure you can rotate them so that the columns, they look symmetrical. The ancient had actually this technique. We find it quite often. And what is important is that this is described very accurately on this inscription, the Elefsis Museum. I will give you the English translation. So the blue one says it should be, should make the poles round. Further down in pink, it says he will use 12 parts of a copper alloy from Mario. Mario is a city in Cyprus known to be a copper producer, consisting of 11 parts of copper and 12 of tin. Now this is exactly the recipe to make bronze. He will deliver the frames straight and squared. These are the empolia. The poles should be ground round. In fact, it uses the word lathed. The word is tornado, the word that we use in modern Greek as well. According to the specimen, so he was given a specimen, and he should assemble them with the frames straight and rounded everywhere, so that when they turn, they rotate evenly. We realized that we were talking about the lathe, so they did have cutting machines. Now, do they have hard metals? Again, back to the literature. We found an article by a professor of metallurgy from the United States in 1961 who had investigated some coins from Sparta of 670 BCE. Now he actually measured their consistency. He found that they made of iron and about 0.2% to 8.8% of carbon. Now again, this is how you make steel. In fact, Professor Borst, in an article in the New York Times, he declared that this would correspond to having the atomic bomb of our age. Very important. Now, going to the museum, if you go there, it is still there. On the wall, close to where the Antikythera Mechanism is now, there is a display of the arrowheads that they had found in the Thermopylae battle. So up there, you can see the Spartan arrowheads, and down there, the ones used by the Persians, that they look much bigger. They are much bigger, and they look much more dangerous. However, if you look at them more carefully, you see that the ones from the Persians, they are corroded, they're made out of iron, and they are rather soft. Look at the ones from the Spartans. They're made out of steel. Now, if you can imagine that if they had the armory was made out of steel, then even if the sky turned black from a large number of the Persian arrows, they wouldn't pierce through the steel armory. Well, I'm not going to say anything more about it. You realize now that the ancient Greeks, they did have both cutting machines and hard metals to be able to cut gears, etc., etc. I apologize because this talk lasted a bit longer. Thank you very much. I didn't see anybody looking at his watch, not even putting his ear to see if it works. Thank you so much. I will stop here. I will give some questions, some of them I have answered. Thank you very much. Somebody please ask questions. Or, yeah, Norbert.
Yeah, okay. We open the discussion, and I'll come around with the microphone. Who starts the discussion? Yeah, the obvious question, the obvious question, of course, is: are there any other artifacts, even remotely resembling the Antikythera Mechanism in antiquity? And if not, why not?
The question is there only one Antikythera Mechanism? Up to now, yes, we have a statistic of one. However, I strongly believe that there must be more, probably lying at the bottom of the sea in other shipwrecks. Maybe. We know that 90% of the bronze items in our museums, they come out of the bottom of the sea. Bronze was a very precious metal, and they would recycle it. So maybe there are other Antikythera mechanisms that they became plates, tin plates in houses in ancient times. So there must be more. In fact, I think it was not built as one piece. I have the feeling, and this is Michael Wright who mentioned this first, that probably they built the front side first, showing the position of the sun and the moon. And then somebody thought, my goodness, if we extend the shaft of the moon to the back side, we can have the Metonic and the Saros cycles. So they joined together and they made the Antikythera Mechanism. An idea.
Is there any ideas who designed it?
Who designed it?
I mean, who makes it? It's also a question, but I think that's probably not so important, but who designed it?
Yeah, we have not found the made in China yet. We know that they had the best laboratories in the world, as I explained, but we have not found anything else, except that we know that Hipparchus lived and died in 120 BC, about the time that the Antikythera Mechanism was made in the Rhodes. maybe you can see his shadow there. We have not seen any evidence yet.
How long would it have taken to make the Antikythera, given that they had the design, so to say, like
How long did it take us to make it?
No,
The engine. Well, as I said, probably it was made in several stages. I'm sure, first of all, I should state that the astronomy inscribed on the Antikythera Mechanism and preserved there is well known. We know it from descriptions, scripts, engines, etc. The technology is very important. The technology is something that is very new. How long did it take? I don't know, but probably starting with astronomical knowledge, there's something maybe wanted to preserve this. In fact, I'm writing an article for Nature Astronomy right now. I'll probably finish it tomorrow here. And I'm making a graphs thing. And there we state two things. It could be either because somebody wanted to preserve the astronomical knowledge of the time on the Antikythera Mechanism, and at the same time it could be used as an educational instrument. You can imagine Hippocrates with his students up in the stadium at Rhodes, if you have been there, explain, well, let's see what we're going to have the next eclipse, and then explain, etc. I'm sorry, it was not a nautical device. It was not used for marine in the sea. Yeah.
Considering the precious material and the precision, it must have been extremely expensive. So I don't think that there should be very many to be expensive.
Okay, you are right, yes. This was probably the toy of the rich and the archons. But whoever had it had power because she could do predictions. And this is what Stella Drew, the archaeologist of our trio, of our Thessaloniki team, very often explained to us. My goodness, you say, what on earth have you found there? It is something very important. You're right. Yes, not very many, but I'm sure that we made a few. Mistakes they must have made as well. We have made mistakes, and the ancient must have made mistakes as well.
Is something like this mentioned in any antique texts?
Who's talking?
Is something like this mentioned in any antique texts? Because we have many texts from the time.
Okay, let me go ahead and find, because I should see, you probably notice here that this is slide 73. This is how many slides I have. But according to my audience, I choose what slides I have. So yes, they say a little bit of something. So there are two pieces of writing from Cicero. One of them is, he says that he saw at the house of Marcellus Jr. He was the nephew of Marcellus the Elder that captured Syracuse. In fact, the soldiers killed Archimedes. He saw a sphere that a Roman soldier, a clever Roman soldier, could use to predict the position of the sun, the moon, and the planets. And the second citation by Cicero is that he saw a device at the house of his friend Posidonius near Rhodes. We know that he went there in 97 BC with similar characteristics, so to predict the position of the sun, the moon, and the planets. At this very moment, we are trying through the TLG to find all the words about sphere, investigating if we can see something more. Also, I did find recently, very recently, about a month ago, again looking at TLG, the word trochiskos, this little wheel, multiple trochiskos devices that were dedicated to a temple. So I wonder if the Antikythera Mechanism was ever dedicated maybe to the Dodona temple. It's too early to say something, so this is going to take another, maybe a couple of years before we collect all the evidence.
These references from Cicero and the fact that he saw a soldier using it, etc., etc., can all those things point towards the fact that A, it was not very expensive, it was industrially produced, so that it was well spread, and etc., and hence not very expensive. Plus the fact that I suspect that you haven't found any signs, although that's already found in a shipwreck, but have you found any strong evidences that there have been mistakes that had to be corrected during the construction? Or was it one go, which would mean that people have been gathering experience in producing it again and again without mistakes?
Yeah, that's a very important question. We hope to be able to answer it, but we have not found any such evidence as yet. So we conjecture that the Antikythera mechanism was built slowly and advanced every time until it reached the stage that we have found it. And maybe other ones that are around. But when I mentioned this cut of the gear with a spin and slot, we thought, yes, we do have something that had to be repaired. But that was eventually not so.
Is there any small probability left that the mechanism is more recent, that the dating is wrong?
That's a good question. Maybe somebody actually dropped it there. The answer is no. As I explained, the coins found on the Antikythera on the boat were pretty old. And because of the letters inscribed on the Antikythera mechanism, there is an upper limit. And for example, the Greek letter pi, we write it with 2 equal legs. Now, in the Antikythera mechanism, I have skipped the point that I showed all the letters. In the Antikythera mechanism, the right foot is shorter and wiggles outside a little bit. Now, this type of writing of the letter pi never appears after 100 BC. Also, the letter M is not written like this, but it's written like this. They all have sheriffs. You know the letter type sans serif, which has sheriffs everywhere. This is how it was made. The omicron is a bit smaller. What else? There must be other reasons. This is not the work was done by epigraphologists mainly.
You mentioned the fact that there are several models, like plexiglass devices, that are reconstructed from museums. So how many of them are in use? Are they fully functional? Or is there any, maybe a digital simulation for people who are interested in seeing the mechanism at work?
Yes. Most of the models that have been asked by the museum was exact replicas of the ancient machine. Operational, but one-to-one, made out of bronze, and this got most museums like. I do not know how many you have, but less than 10 up to now, maybe around 10. This very large one, that is three times as high, 3 times as large as the Antikythera mechanism, already operates at the Observatory of Athens, the Astronomical Observatory of Athens. A second one is being built, maybe it is ready now, it's going to go to China. And this is mainly our mechanical engineers to this. I don't know all the orders, but very soon a page will be up with all the models that can be made, and then somebody can come to communicate with our university. All these models, they're under the aegis of our university. So they're professionally made.
So you mentioned that there are instructions how to use it, right? Like on the doors, as I understood. Is it in Greek?
All the letters are Greek letters, all the letters.
No.
Even if the names are Egyptian, the letters are in Greek.
Yeah, so my question actually, so letters are Greek and instructions are in Greek.
Yes.
So you have understood what is actually written there?
Probably I should do another investigation to actually show you some of the letters, because two people have asked me already. Now I have to go back slowly. Okay, this is the question of time. Okay, this is about the spirals I didn't talk about. Where is my letters? Maybe I skipped them already. If I don't find the next 2 minutes, I will not go. No, it's not here. Sorry, I skipped it. All the letters are Greek letters, all the sentences that we have, all the letters, the words and the sentences that we have decoded are proper Greek text. And because it's only 200 years BC, I can read it myself, although I have done very little ancient Greek. But the Greek language has not developed very much for the last 2,000 years. It has developed quite a lot for the last 2,500 years. So I can read everything.
And what is the purpose then of these names of Egyptian, of the months, which are written with the Greek letters but actually in Egyptian language? So what is the purpose? Is there any idea why they have done it? In order to use by Egyptians? Or?
Yes. Well, I don't really know, but I have been asked this before. My answer has been that the letters inscribed, in particular the Metonic spiral, they have certain names that lead us, that is obvious, that they're all Corinthian months. Unfortunately, the Corinthian calendar is completely lost because Corinth was completely destroyed by the Romans because of its resistance. However, the colonies of Corinth are there where we can type this. I think we can find somewhere here. Yeah, this is it. Okay. So let me show you this. In fact, okay, this is also good enough to show you the. So these are the names of the months that we see there. In the next, the next one will be here, should be here. Come on. These are the letters that we have for the months. And you see, these are the month names of the Antikythera Mechanism. This is from Corfu, Kerkyra, Dodona, Vustrotos, this is in southern Albania. Tavromenius is in Sicily, that was the closest, the other which is closer but not that close. And unfortunately nothing from Athens, nothing or very little of Rhodes. So this is how we use the letters. Maybe to show you also where the cities come from. The cities are from northwestern Greece, maybe. Maybe you can talk to me. I don't feel very comfortable that I have fully answered your question. Maybe we can talk later.
To summarize all this, what is the state of knowledge about the completeness? It's me again here. The state of completeness we have. I mean, I've seen reconstructions 20, 30 years ago. There was a nice one in the museum in Athens. I think it's now superseded. How much would you think or feel of the gears we know by now, and how complete is our understanding of the complete mechanism? Or can there be major parts that are still completely unknown at this point?
Even if we have a third of a gear, this is enough to know how many teeth it has. So I think we have found more or less all the gearing except the planets. We have not found any planetary gearing. If the planetary gearing was there, it was at the very top, maybe a rock came and shaded away, then the mechanism would have about 72 gears, a very large number. On the other hand, even a missing gear can be calculated. For example, if you want to make a calendar, it's a weekly calendar, you can have a gear of 365 teeth, engage it with the gear that has only 7 teeth. Now when the first one rotates by 7 teeth, this makes a full rotation. If it has a pointer that shows Monday, Tuesday, etc., then you know you have a weekly calendar. If the second gear is missing, but you do have the pointer, you know what the first gear does. So with this, I think there are about 5 gears that we have not found, but it's absolutely obvious what they did, and this is why we have reconstructed the Antikythera mechanism. In our model, we have not included the planetary system because no gear has been found yet, although the names of all known 5 planets in ancient times are on the inscriptions, so Mercury, Venus, Mars, Jupiter, and Saturn, but we have not included because we have not real evidence as yet. Once we find the evidence, we will be sure to include it as well in our models.
Is there a publication of the text of the manual size?
Yes.
And could you say when has been published?
There's a publication, a very first attempt was made with an article in Nature back in 2006, I think November 2006. However, recently, the full description, properly done with the Amsterdam Convention, had been published. The publisher is called Brett Pauls, and it was last year. Now, it's probably, I think it's called the Antikythera inscriptions fully read or something like this. Brett Pauls, you probably know that. You can find it. Thank you.
Thank you.
So maybe all this information is useful on the Antikythera project website where all the literature is collected?
We put on our site whatever we are allowed to put on our site. So Brett Pauls has not given us the permission to do so yet.
But that's a very informative website, that's why I'm trying to mention it. So.
Yes. It is a book, really. It is probably a full issue of one of the journals. The journal is called Almagest, I think.
Okay. No, I think we are through. I would like to thank John once more for a very inspiring, very interesting talk. Thank you very much.
Thank you for being here. I'm very glad that you stayed for such a long time for this lecture. Thank you.
Just a final remark, which is, this was an astronomy talk, but without our ordinary series of talks, but this series of astronomy talks here in the Deutsches Museum Bonn will also be continued later this year. And the serious topic this year is extrasolar planets. And we have prepared 3 talks presented by Thomas Henning from Heidelberg, by Heike Rauer from Berlin, and Michael Kramer from our institute on different facets of extrasolar planets starting in October this year. Please stay tuned. Thanks a lot.
Also das Deutsche Museum möchte sich herzlich bei Professor Seiradakis bedanken. Und heute hat man wieder gesehen, wovon unser Museum lebt, von der Neugier unserer Besucher. Und ich hoffe, wir haben die auch wieder diesmal ein Stück stimmen können. Und wenn Sie noch weitere Veranstaltungen finden wollen, abonnieren Sie einfach unseren Newsletter auf Ihrer Website. Vielen Dank. Guten Abend.